how much current goes this way? How big is a voltmeter? What's the resistance inside a voltmeter? Is it infinite or is it nothing? It's infinite, right? We don't want to change the current. So no current can go this way. So if I put 2 probes here, how much voltage is being consumed in this little R right here? There's none, right? There's no current. So this voltage is actually the same as the battery's voltage. That's E. But if I close this switch, now some current can start to flow. And when current flows through this resistor, what happens? There's some voltage consumed, right? There's some voltage drop right there. So we don't know how much, but if there is some current, then there is some resistance that drops that current. So this has got to be C, right? That is why. It's tricky. Anyone got a question on that one? Now that you saw it?
Oh, wait.
This was the killer of souls. It wasn't as bad as number 10 though. Number 10, which I didn't think was as hard, but that's only 15%. 15% of folks got number 10, and here's number 10, in case you're wondering. So probably, maybe you made sense of it after you saw what the answer was. When you hook batteries in parallel, what does that do? What does it do when you hook batteries in parallel? It lasts longer. And why does it last longer?
Voltage.
They share the load, right? I only have to put, so if this takes a certain amount of current, I share it. Half of it comes from here and half of it comes from here, right? I get half and you get half. We share the load together. So if I do that, it tells us, let's see. So how much of the total current is going through one? Half. How much of it's going through two? Well, half goes here and half goes here, so half, 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 half. They all have a half of the total current. So these are all the same.
Oh, they're all the same one.
All right, all the same. They all have half of the total current. Lauren?
Wait a minute.
Okay, I'll be back in a second. Don't let me take up the test without
All
changing
one
it.
half. All one half.
All right. If you want to know how your grade was calculated, to make sure you got the right number in the grade book, you got 76 on the test for partial credit and FRQs and everything. So you start with a 76. And then you get 0.5 points for every one you got right. Right? So you should be able to do something like this. 0.5 times the number correct plus 76. That's what you have. So make sure that's what you got. The grade in the book really shows that. And if that is right, then I will take the paperback.
I know the last
Do I have to pull out my calculator for that? I don't know the total. Oh, total number of questions is.
All right. Thank you. The most powerful force by far. And it's called, yeah, so we know about gravity, right? Gravity's strong. I'm going to show you how this force compares to gravity in a little bit. It's like hundreds of billions of times stronger or something than gravity. It's really strong. It's called electrostatic force.
Oh. I was thinking like you were going to say.
And so, what do you know about chemistry and atoms? What do you know?
The bond is very strong.
They got electrons and they got protons. And since electrons and protons have opposite signs, what happens to those two things? They attract, and they attract extremely strongly. That force of attraction is very, very, very strong compared to gravity. So let's start with you and your partner chat this out.
Caramel.
Let's see.
Where did you go? I'm joining Noel's partnership.
Just answer the question. You don't even have to write it down. Just answer it any way you can.
If A attracts B, B equals C, C equals
See that? Yes, I can. So you have A, B, C, right? If A attracts B, B repels C, C repels D, and D is negatively charged, what is the sign of A?
So A attracts B,
Yeah.
B repels C.
Wait, so opposite signs repel or
So that-
attract?
Opposite sign
Opposite attract.
So
Okay, so A and
must
B.
be because it repels B, right?
B, C, and D must be the same sign, right?
So A is
A is, so A is positive, B, C, and D are negative. A is positive. Okay. Okay. We're either very smart or very not. I think we're the first. Let me. There you go, Amy.
You said B for 27, but you got C for 28. So you got one half.
I feel like I'm a school.
You get one half of it.
Are you like, oh, you're
I'm recording it for her because she wanted like a recording of like class.
Do you see what I'm saying? You got one for 3.
Hey.
Positive.
So where do we start? D. D is negatively charged. What happens to C? C repels D, so also got to be negative because it repels. What about B? Also negative. And then what does A do? A attracts, so that's got to be positive. All right. So it's just a game. I mean, you've been knowing this since you were little. Maybe you've done it with magnets. The same. Who's ever played with magnets before? Yeah. You know what magnets are? No. You don't know what magnets are. It's our yeah.
Magnetized ferrous metal.
But what does magnetize mean?
It means that like most of the atoms on one side are negatively charged, most of the atoms on the other side are
That's
positive.
polarized.
electros.
No.
Okay.
That's like for second grade, y'all. Don't do that. I'm not trying to. It's
Is it something to do with the poles?
it's. So say it again, Andrew. You might be onto something.
I said that like on one end of the magnet they're negatively charged, on one end of the magnet they're positive.
So that would work for electrostatic force, right? But magnetic force is actually it is something to do with rotation.
Yes. You got some
It's weird, y'all. And you know what? It's our 5th unit. Everybody, we talked about magnets. You don't know what a magnet is. It's crazy, right? We'll talk about magnets later. It's a shortcut word. It's not really a new phenomenon. It's not a new force, right? But you put that aside. This is the force we're talking about today, electrostatic force, right? So these behave in this way. I'm going to show you something fun. That you can quantify. You can actually find out how much electrostatic force is. So let's go on a scavenger hunt. Pull out your formula sheet. Try to find the formula for electrostatic force.
Okay, we're finding the formula. Okay, this is unnecessary.
Formula sheet.
In the
Right side.
I can see it.
The top right?
The middle right.
Top right.
It's the very first equation, right? It's the very first equation. They hide it. Why do you think they hide it at the very first? It's really important. It's in fact the most important. So the unit we're about to start is the largest unit that will take the most time and has the most discipline. All right. So electrostatic force, and it looks really. Oof. I think they say like this. Don't they say 1/4 pi epsilon naught Q1 Q2 over R squared or something?
Bravo.
Is it? Yeah. So absolute value where?
Of Q1, Q2.
Okay. All right.
In the denominator.
Oh, the whole thing. Okay. So, that looks like you want to throw up in your mouth a little bit, right? It's bad. It looks bad. In a few minutes, we're gonna take this thing and we're gonna understand it completely. It's not as bad as you think. All right. You have to really get it. Yeah.
What's the arrow on top of the F?
The arrow means vector. It's here. It just means it has a direction. All right. Y'all know that force has a direction. Like which way is gravity, for example? Down. So that's what the vector means, right? It's not just all right. This is the first part I don't like. I'm a little bit late. I mean, shortcut oriented, and I don't like that, and neither do other people. So I want you to find a value for that. I want you to type that into your calculator. Hint, there's values for constants on the back side of your formula sheet. All right, so type in that value. Tell me what it is. Show me on your calculator, and then I'll believe you. I think there's one on there that you do know. It's called pi.
It's vacuum permittivity.
Get it? What? No, watch it, Dale. You gotta do it yourself or hands on.
It doesn't look like this.
That's right.
Yay.
Yep. That's right. So, if you're serious about being good at physics, you're gonna start to be good at the fraction bar, y'all, because you're gonna have lots of things. And of course, parentheses are fine if you're really good at it. But there will be times that the formula rolls off the screen and it's a hot mess. So y'all use the fraction bar. It's either, if you have the newest operating system and the thing calc, you get alpha x done, right? If you have the older operating system, you just hit alpha y enter done. You're done. It's quick. It just takes you a few seconds. Use the fraction bar. Seriously, get started on it now, because when the going gets tough, you're gonna sink if you have all these parentheses all over the place. Now, I said it's 1 over, and look, when I use the fraction bar, I can totally see that I got this like really neat, right? I can definitely see, there's 4 pi. 4 is not fair either, because my calculator is a lot harder to do. 4 pi. Epsilon naught. What is epsilon naught? Vacuum permittivity. What does permittivity mean? What does it mean for something to be permitted? It's allowed, right? Hey, anyone ever use what's this called? Wi-Fi? Anyone ever use this thing? In fact, I think it's in this room right now. This room has high permittivity for Wi-Fi. It can float through the air, right? Is this room a vacuum?
No.
No, we would all be dead, right? You have to breathe air.
That would be cool.
So Wi-Fi permeates this airspace pretty well, though. Does Wi-Fi permeate the cinder blocks?
No.
Yeah.
Yeah, it does pretty well.
Not as well.
Not as well. Not as well.
Frankly, my
For some reason, whatever's going on in the bathroom, I don't know if they got more metal in the walls or something, like it's not a very primitive area, right? There's low permittivity for Wi-Fi in the bathroom.
It's a signal jam.
Yeah, signal jam. I don't know what it is. Fine.
It's just Franklin line.
So permittivity is about that. It's about how well something can travel through, all right? Now, vacuum permittivity is the very lowest possible resistance. That means there's no particles in the air, and these electromagnetic waves can just zoom in through. You don't really need to know what that means, okay? But when they say vacuum permittivity, and what's the unit for that anyway?
Coulomb squared over newtons per meter squared.
Wow. Is that a hard unit to picture in your mind?
Yes.
Coulomb squared over newtons per meter squared. I don't even know what that means, right? So basically you need to know it's a constant that people worked really hard to figure out. And it's on your sheet, you never need to memorize it. And it has to do with how stuff can like permeate through space, all right? Now, we use it so often. Oh, and tell me what the value is, by the way. I don't remember it. Someone read it off to me.
89918
No, the E. 8.85
times 10 to the negative 12.
times 10 to the negative 12. Wait a minute. My calculator says EE. Why does my calculator say EE and not E?
It's So there's another E.
Yeah, it's just a notation, right? This EE is the calculator's notation for 10 to the power of, right? 8.85 times 10 to the what?
Oh, negative 12.
Negative 12. All right. If I hit enter, I get this thing. Not much better, right? Not much better. It's a big number. It's weird. But physicists have said, you know what this is? This is actually 9E9. And that's what we'll use. 99. What does that mean?
99.
9 billion. It's a really fun lesson, sorry. So we use this 1 over 4 pi epsilon naught so often that we're going to call it 99. And some of you have noticed, what do they have? They have another name for that on the back of the sheet. What's that called? Coulomb's law constant. So we just say little k equals this, and we're done. Coulomb's law. So Coulomb's law is the thing that we just talked about. We'll talk about it more. Q1, Q2 over R squared. So y'all, you never have to really remember this piece again. But we're going to use K all the time. K is not an experimentally derived value, but epsilon naught is. They figured out how to find this, and they just use this as like a placeholder. I'm going to show you something cool in your calculator. If you ever need K, go make sure on the home screen, you have that right there. Hit STO. You're going to store it in K. Where's K? Above the parentheses. So I hit alpha K and I hit enter. Now that number is stored in K. It will always be there unless you reset your calculator. So now if I just hit K, if I hit alpha K, enter, it just comes up with that. Actually, don't store that one. I'm sorry. Store 99. So here's what we're going to do. We're going to go 9E9 and we're going to store that in K. All right. This is actually a better number, but this is what they use on the AP exam. So 99 store K. You push this button, it's called store. It's okay. Most people have never used it. Luke, it's not. I mean, who's ever used store before? Yeah, most people don't use it much, right? So if you use it a little bit. So now if I want to like 6K, I just type in 6K, and it just, I get that, right? I don't have to ever type in the value for K again. It just has it in there for me. Okay. You learned something about the calculator. You learned something about permittivity. Y'all okay so far?
Yes.
So we're deciphering this thing, which is called Coulomb's law, and we're trying to make it a little simpler all the time. All right. It said Fe is equal to K, right? Doesn't it look better already? Q1, Q2 over R squared. I don't ever use the parenthesis M and the absolute value. Because you know what? This is the one unit where commonsensical, because the direction, the positive or minus sign is just direction. But can't you always figure out if these things are going to be going towards each other or away from each other? How can you figure that out? They're signs, right? If they're the same sign, they're going towards each other. Sorry, if they're the same side, they're repelling, and if they're the opposite signs, they're attracting. Okay, so I'm gonna move it down to this. All right. So now this looks a little better. It's a little bit peculiar though, in the fact that the two charges matter, right? Any two charges, I have this +3, and I have this -2, right? What are these gonna do? They're gonna attract. So this guy has some Fe this way, and this guy has some Fe this way. Which one has the stronger Fe here? Close left. Look at the formula. How do I calculate the Fe for this guy? I multiply the 2 and I divide by the radius between, right? How do I calculate the formula of the Fe for this guy? I multiply so which one has a stronger Fe? They're the same. Newton told us that, equal and opposite forces, right? But you can also see it from the formula. So it doesn't matter. If this guy's really big, he's not the only one that gets a big force, right? You also get a big force. It's like, all right, you're on the football team, this guy's on your team, that's great, we all win, right? Everybody gets the force, even if just one of the people is big. All right? That's not the peculiar thing. The peculiar thing to me is this. it makes sense to me that the force goes down as the distance increases, right? So it makes sense that r is the distance between. Doesn't it make sense that they get further away, the force goes down? But this r squared, why is it squared? Huh. Let me show you. Someone I knew drew a picture of this. It's pretty neat.
Gotta be some like area, but
Yeah, it's actually it is that. So, what is it called? Like famous in a small pond or whatever. This guy, did this little thing. This is on the AP Classroom, by the way. I watched it last year, and then this summer when I went to grade AP test, guess who I met? This guy.
oh,
Yeah,
You
I was
know
like,
that?
oh,
Was he cool?
that lecture that you gave. He's like, oh, I didn't even know anyone watched that. So it was cool. Look, you're gonna get 30 seconds with your partner. This is explaining why it's r squared. Okay, go talk to your partner. What's that mean?
I don't remember, but I really remember seeing this in math. Which doesn't help at all. But it was from this area. It was like later on in the year, I think. It was between gravitational. It was gravitational pull.
Oh, yeah, and it was like, it was when we were showing if something was like blocking the stuff, it's still pulled by the ground. I don't know. I remember what you're talking about.
Yeah, no, that's where we first saw that. So it's r squared because 2r.
there should be a little bit of time though, right?
Because like r,
Like it's not like a.
because r times r is added each time, each like, I don't know how to explain
You
it.
think it'd be like full.
As it like expands.
This over time.
What are you lighthouse?
This is my favorite. Like I've known about this, and it's called the inverse square relationship, right? Inverse squared. This is a really great picture. Your influence gets diluted as you get further away, right? Your influence gets diluted because you have to spread your influence over this if you're 1 unit away. But if you go 2 units away, it's also 2 units that way. It's an area. Like your whatever it is, in this case electrostatic field, has to spread over an area. And then if you get 3 units away, how big is this area now? 9, right? So it's 9 units. So it just gets more and more diluted. And the way I can think of it is like this. I have this projector here. In the beginning of school, I had to make some decisions about it. This is so my source right now is going to be the light from the projector. All right. If I make it close, if I change the R to get very close, you notice that it's smaller but brighter, right? The influence is brighter. It's more higher magnitude but smaller area. But if I take this guy and I slide it out, what do you notice? As its area gets bigger, what happens to its intensity?
Lowers.
It decreases. So this is really cool. I like having this giant screen, but it's hard to see. So I had to what is the middle path or whatever, right? I don't have it super close and super sharp, but I don't want it way out here. This is a very clear example of the distance, and you can't tell that it's squared, but I promise you it is. So if I go somewhere back in the middle, like somewhere in there, it's both big enough and bright enough. Okay? I was lucky enough to see this. Has anyone ever been to the Exploratorium in San Francisco? If you ever go to San Francisco, it's down in the famous part of town. It's awesome. It's like a children's museum to end all children's museums. They have this thing here, and they have a little pin of light, and then they have these squares, and you can set it out at 1D, and then 2D, and then 3D, and it has this thing, and you can see the size gets 9 times bigger at 3D, but the brightness is way, way less. So they actually have a grid on there so you can actually see exactly how much it is. So this inverse square relationship depends on light, electromagnetic force, and people who took math last year, what else? Gravity. Gravity, look! Go explore. You're not in mech, or maybe you are, maybe you haven't. Find the gravity force on the other side of the formula. Max, did you find the gravity equation?
Yes.
What is it?
Force of gravity equals G M1 M2 over R squared.
Holy cow! That looks really similar to me. Instead of the size of the charges though, what is it? It's the size of the masses. Did you all know that right now, all of your pencils are being attracted to my expo marker?
Yes.
Unfortunately, I can't grab your pencil out of it because I can sell them all on eBay, but I can't because the force is very, very feeble. Why is the force feeble? What's the M of this guy?
Very small.
Small. What's the M of your pencil?
Very small.
So when I multiply those two things, it's weak compared to, what are we close to that has a really big M?
Earth.
Oh, the Earth. I heard it's pretty massive, right? And so the Earth kind of overwhelms all the gravity things you're feeling, right? I think the Earth is at least 100 kilograms or more. It's really big.
You know.
Now, I want to know who wins on a small level. All right? So we're going to play the game. Let's calculate the value of each of these for an atom. All right? Let's calculate the value for an atom. Y'all got to help me out though. What's K? 99. Q for an atom. That's on the back of the paper. What's Q for an atom? For an electron. Sorry, not an atom. An electron or a proton.
Q. What's Q?
Chart?
Oh, charge.
So maybe something to do
Yeah.
with the electron volt.
One. Okay, so it's 1.6
It's 9
times.
Okay, make sure.
Oh, you didn't kill it?
What's the charge of an electron? It says there. 1.6 times 10 to the what? Negative 19. What's the charge of a proton? So let's do a hydrogen atom, right? We'll just do a hydrogen atom. Here's the proton. Here's the electron. What's the charge of it? This is the charge of the electron. What's the charge of the proton? Same, yo. They have the same magnitude of charge. Maybe you didn't know that. If they weren't balanced, then the whole thing would mess up. All right. What's the typical distance from the atom? You probably don't know that, but I can look that up for you. It's 0.5 times 10 to the negative 10th. All right, don't calculate it yet. Let's fill in the other one first. Let me move this over here. We're gonna see who's the boss. G M1 M2 over R squared. What's the value for G? Oh, the capital G.
6.67.
What's the mass of a proton? 10 to the negative what?
27.
What's the mass of an electron? Oh my gosh. Small.
9.11 times 10 to the negative 31.
Is the mass of an electron 0?
No.
Is it very much?
No.
Not very much. And then what about the R? That's the same R, right?
Yes.
Okay. Calculate these two. And a word while you're calculating. You signed up for a class that is heavy in detailed math, right? These things are very tiny, the numbers are very huge or very small. Be proud of yourself and say, you know what, this is hard math, but I can do it. Use your calculator, get a fraction going, type these things in carefully. Everybody do it, don't watch your neighbor do it. Hands on buttons, Laura, hands on buttons. The numerators. On the back of the sheet, this tells me the charge of a proton, the charge of an electron. All these are coming from the formula sheet, except for this. I looked this up for you. This is not on the formula sheet. But that's the distance here, right? That's R. an atom?
We never learned that.
Like a sphere.
We always talk about this in
I don't know what they
biology, like
teach
what
me.
an actual atom is.
Sorcery, actually.
Because like how you said in biology, I remember they said the model isn't like
Yeah.
it, but what is it?
Just keep knowing. I want to see an atom. I want to look at it.
All right, did you get a
know how they
value?
do the thing where they like draw with atoms? Like they put it under the microscope and they can draw with atoms?
I've never seen that.
I swear, it's like this like, okay, you gotta search it up. It's like atom animation on YouTube. It's probably, I'm pretty sure it's saying, like, I'm not going crazy.
I'm gonna look it up.
All right. Christina, what'd you get for this one?
I got 9.216 e to the negative 8.
All right. Is that a very big force?
You did.
No.
Thank you.
That's one. That's only one atom, though, right? How many atoms do you have in
Billion.
your body?
And
More than a dozen, right? So you start multiplying that by huge numbers, the forces get pretty big. What about gravity? Let's see. Luke, what'd you get for the gravity?
4.059
I didn't get 15.
Is that what we got?
Wait, did you get the same?
I got 4.05, but I didn't get 15. Negative 47 is what I also got. Which one's bigger? Electrostatic force is how many times bigger? So take this divided by this.
come on now.
A lot. Wait,
That's
no.
a lot.
Well, yeah.
It should be a lot.
Well, that's not a very big number, but.
It's a big number.
What did you get?
Oh, I don't know if I did this right then. But what am I supposed to I'm supposed to divide it the other way around. Oops. That may be an
I
issue.
want-
That's a big number now.
I want FE divided by FG.
Okay.
How many times?
2.27 times 10 to the power 39.
39. Okay, so it goes million is 6, billion is 9, trillion is 12, quadrillion is 15, quintillion is 18, sextillion 21. How big is this?
Very.
What?
How many is 39? How many is? It's a number that you can't. It's like it's so much bigger that basically gravity is like insignificant at that point, right?
Yeah.
Gravity is like almost doesn't even matter. They're both calculable, and if you get rid of this, then that becomes the biggest force, and then this all of a sudden becomes important, right? But we want to see here that on small scales, who's the boss? Electrostatic force is the boss on small scales, right? On small things, and how many things happen on small scales? So many, right? It's just so many. And, you gotta be a little brave here with the calculator and these big numbers. They seem overwhelming at first, but it's almost like you gotta be an accountant a little bit. You have to type them all in, because look what happens if you leave off one negative sign. It's completely crazy, right? And that's totally a normal thing to do. Just don't. Right? Don't do that. Just get good at it. I don't know any other way to say it. The way that I get good at it, and the reason I stress so much typing it in with this fraction bar is because I can look at each term after I've typed it and then I get it in. Right? If you look at each term, that's about the best you can do. Even better is when you like work in a partner as a pair and you both do the same thing. That's even better. All right. How you feeling so far?
Good.
There's a force out there, electrostatic force, that either repels or pushes or attracts things very strongly. Okay? Your turn to practice. I want to know the values of some electrostatic forces. How about random partner? That'd be fun. You've been sitting in the same spot for so long
I
now.
follow College Florida.
Who
Instagram.
left? Some people left. I
And
don't know
they
why
posted,
everybody
they
wanted
would
to leave
post like
today.
post and be like, give advice on
Yeah, like
this share advice on this course or whatever. And the one for AP Physics was like, just don't take it. And I think that was like AP Physics.
That's why I'm ballpark here. Let's take our time on this one. This is kind of like we're building our base right now. It says the magnitude of the net force on sphere A. So sphere A, there's this thing, has anyone heard of a thing called superposition?
Yeah.
What does superposition mean?
Doing something's in multiple locations at the same time.
You can do each one separately and then add their effects at the end, right? So you keep each pair. So we're gonna take A and B as one pair, and then we're gonna take A and C as another pair, and we're gonna add them at the end. And that's a thing that's allowed in lots of science. So we can use superposition. So let's do. So here's A. Which way is the force on A and B? Which way is on A between A and B? Which way is the force gonna go? It's gonna go this way because this is the force between A and B, right? Why is it gonna go that way? It's being attracted to B, right? But what about C? It's being repelled from C, and why did I draw it short like that? It's less. Well, I only know it's less because I've already done it, but why do you think I think it's less?
Because it's further away.
It's further away, and in the formula, what's squared? Distance is squared, right? So the distance is really important. So I think it's gonna be like this, but once I do the numbers, I can look it out, right? So here we go. The force, electrostatic, is K, Q1, Q2 over R squared. This is 9E9. What's Q1? For do this, let's do A and B first. 3 micro, which is E negative 6, yeah? Times 1.5 micro all over 0.2 squared. This is a negative 6. All right, when I type all this in, I think I got 1.01. Yep. So this was 1.01 newtons, this side.
Wait, okay, let me check.
All right, let's do the force E for BC. K, Q1, Q2 over R squared, 9E9. What about Q1? Same thing, right? 3E negative 6. What about Q2? 4E negative 6. And what about R?
Wait, no, wait.
0.6 squared.
Oh.
I think I got 0.3. And 0.3 is this guy, right? So what's the net? It's 1.01 minus 0.3, 0.71. Which way? To the right. And you may be like, Mr. Walters, that was picky. I got it to the left. It really matters, and we're learning about it. All right. So a couple groups got that. I'm sorry for you that got it. You were on the right track. You just got it wrong. So you were good at trying to build a bridge. It just fell into the river. But it's no big deal. No one was on it probably, unless they were. Give this partner a high five. You gotta do the backside with another partner. All right, another chance for my sticker. I'm feeling generous today. Feeling generous today. I draw this out and I know the direction. Do y'all believe that this charge, if this is charge C, let's do this, right? This is charge C, and then this is the other one. This one stayed the same, and that one doubled. What about the radius? It was 3D. Now it's 2D. So what's the change? 2/3, right? The radius went down to 2/3 of what it was before. Now watch the math. You know what's on the top? 2. What's on the bottom? 4/9. People are like, oh, compound fractions. I hate compound fractions. Well, this is the same thing as 2 divided by 4/9, which is the same thing as 2 times 9/4, which is what? Yeah, 9/2 or 18 over 4, 9/2. Is 9/2 the new force? What is 9/2? 9/2 is the factor of change, right? So that's how many times, so what was the original force? 4. So I can say the new force is the factor of change times the old force, right? So factor of change is 9/2. What was the original force? 4. How much is that? 18, right? 18 newtons. The new force is 18 newtons. Which direction is that? 18 this way. What's my net? 14 to the left. That's the easiest way I think we can do it with the factor of change. Another clever way I saw people do it was they solved for d squared. Let's talk about that real quick. That's a good idea, right? If f is equal to kqq over d squared, well, let's fill in everything we know for the first one. What's f? The one we know. 4. K, we don't even care what the value of k is. What's q1? 3q, what's q2? Q over d squared, all right? So now, d squared is equal to 3kq squared over 4. Now if I want to do the new one, f is equal to kq1 q2 over d squared. Well, I need to know the new f, right? K is the same, q1, 3q, q2, 2q over d squared. Well, this is d squared, right? 3kq squared over 4. All right, let's look. Oh gosh, on the top I have, can we agree that the k's cancel out? And the q squareds cancel out? So I have 6 over 3 over 4, which is 24 over 3, which is 8. Uh-oh.
No.
Did I do that wrong? It should be 18, huh? Oh, d squared, d squared. No, that's right, that's still d squared.
Like both, the distance should be 3D and 2D.
Thank you, yes, I did this wrong. So this is 2d squared, which is, this is 4d squared.
Isn't that the 3D one?
And then I just left up the 3d on the bottom, right? This is 3.
I mean, isn't the first one the 3D one?
This is the 3D. All right, so I got sloppy. You all want to finish it? Yeah, we don't have to finish it. So what did I do wrong? This is 3D. So this is actually, we can finish it. I'm in the mood to finish it now. 9d squared. So this is, so d squared is this over 36. Yeah, there we go. Kq squared over 12. There we go. So now, this is 2d squared, which is 4d squared.
Yeah.
Let's try again. So this is 6 over 4 times k 112. So that is 6 over 1/3. That's 18. There we go.
Squared is 4D squared.
Yay.
18. Either way. All right. This is a little harder. I messed it up, right? That's a little easier. Maybe it's a little more straightforward. Either way, it's a hard problem. Give your partner a high five for struggling through it. We'll talk about more next time. Back to normal seats, please. So be careful there. Don't fall in the same pitfall that I fell into.
Did you spawn the same pitfall?